Okay, so in this video, let's validate the parameter beta 1 and beta 1 using hypothesis testing. So the regression coefficient beta 1 captures the existence of a linear relationship between the response variable and the explanatory variable, right? So if we don't have beta 1, that means if beta 1 is equal to 0, we can conclude that there is no statistically significant linear relationship between the two variables, right? In this, so now let's discuss the appropriate test statistic to carry out a hypothesis test on the regression coefficient beta 1. Because if beta 1 is 0, then it's just y equals beta 0. There's no relationship here, it's just linear. So we'll see how to carry out a hypothesis test on the beta 1 value. So look, from OLS and from what we did in the previous videos, we know that beta 1 is equal to, I'll just write it down again, sigma equals I equals 1 to n xi minus x bar into yi minus y bar whole upon sigma I equals 1 to n xi minus x bar the whole square. So this, I can write this as sigma I equals 1 to n xi minus x bar yi whole upon, and the denominator I'll have xi minus x bar the whole square minus x bar into yi minus y bar sigma I equals 1 to n. If you just expand this and you add and subtract it, you will get back this equation. So ultimately this can be written as sigma xi minus x bar into yi I equals 1 to n whole upon sigma xi minus x bar the whole square I equals 1 to n again. So why did I remove this is because sigma y minus the summation of all the data points minus the mean will all sum up to 0. So this entire term, this becomes 0. This is a property of mean. So this equation, I can write this as beta 1 equals sigma I equals 1 to n k yi whole upon sigma I equals 1 to n k square, right? Ki. Now, why am I allowed to write it? Is because Ki is a constant. Since Xi is assumed to be non-stochastic, right? Xi is assumed to be non-stochastic, so this becomes a constant. So I'm going to write Ki over here. Now, since we assume that the error term follows a normal distribution, the yi values also follow a normal distribution, okay? Since the value of beta 1 is a constant multiple of yi, beta 1 also follows a normal distribution. This is again from the properties of normal distribution. Yi follows a normal distribution because the errors are normally distributed, and because beta 1 is a constant multiple of yi, because this is constant, ki is constant, beta 1 follows a normal distribution too, right? This is all properties of normal distributions. So now we want to look, now let me define something called the standard error. Standard error is the standard deviation of a random variable that is calculated from a sample, okay? Standard deviation calculated from a sample is the standard error. So, look, if we go back to maximum likelihood estimation, right? From maximum likelihood estimation, I can say that, you know, the standard error of yi is just equal to the standard error. Wait, sorry. So from maximum likelihood estimation, if I want to find the standard deviation of the population from a sample, we know from maximum likelihood estimation that it's equal to the sample standard deviation. So standard deviation of population is equal to the standard deviation of sample. Okay, if this is a Gaussian distribution. Okay, but here we have only a small sample as our population, right? When we have a sample as a population and we want to find the parameters of the actual population from the sample, which is the population, we we basically use the t distribution, right? And in the t distribution, the population standard deviation is equal to the sample standard deviation upon the number or the degrees of freedom, okay, df, right? So standard deviation for my yi is just the standard deviation of the population upon n minus 2, because I have two parameters here, b0 and b1, right? So now I can write this as standard error of beta 1 is equal to standard error whole upon under root sigma I equals 1 to n, 1 to n, xi minus x bar the whole square, right? Why am I allowed to write it like this? See, I have this over here. I can either cancel this and cancel the square, or I can just take the square root over here, correct? It's the same thing. So that's why I've written it like this, okay? I hope you understood the standard error part. Um, it's just maximum likelihood estimation. That's how we are estimating it. So the standard error, so this is basically, so if I have to write it over here, it's basically the standard deviation, which is sigma under root I equals 1 to n yi minus y bar the whole square whole upon n minus 2 whole upon sigma I equals 1 to n xi minus x bar the whole square. Okay, this is what it becomes, the standard error, right? Now let's carry out a hypothesis test. Okay, so my h naught here is that there is no relationship between x and y, that which basically means that beta 1 is equal to 0. My alternative hypothesis is that beta 1 is not equal to 0. That means that there is a relationship between x and y. Okay, so the corresponding t statistic will be given as beta 1 predicted minus beta 1 whole upon the standard error of beta 1. Okay, this is similar to what you have in the standard normal variate for the Gaussian distribution, x minus mu upon sigma, when we calculate the the p-value for our standard normal variate to see if it passes the hypothesis test or not. Okay, this is very similar to that. Now, since my alternative hypothesis says that beta 1 is equal to 0, that is what I will consider my beta 1 to be equal to 0, because we start with an assumption that the null hypothesis is true. So ultimately, my t statistic is nothing but beta 1 hat upon standard error of beta 1. Okay, this is my t statistic. So once I take this t statistic, I can use the degrees of freedom to find the value, and then I can find the particular p value. Okay, when I find the value of the t statistic on the x-axis, suppose this is my t distribution, let's just say, and this is my area level of significance, 0.05, alpha equals 0.05. If the t statistic falls here, I can find the p-value over here. This will give me the p-value. And if the p-value is less than 0.05, then it means that my null hypothesis is wrong. So we reject the null hypothesis. So that is how you do a hypothesis test in linear regression to validate your parameters.